Yes, ma'am.
Hello. I hope it is
Yes, ma'am. It is visible.
in PPT mode.
Yes, ma'am. No loading.
So, good morning to all of you. So,
Ma'am.
sorry.
Good morning, ma'am. We may start, ma'am.
Okay, is it visible, right? The screen?
Yes, ma'am. It is visible.
Okay, okay. I welcome you all to this course, which is basically Chemical Engineering Design 2. Design 1 we have already done in the last semester. And I hope you all have got the basic idea about that design. It was related to basically stress and strain relationship. Okay, in short, mechanics, the material we have considered there. So that was the we consider any I don't know why echo is there. Hello,
Yes, ma'am.
you are able to uh, listen properly, or is ego there as well?
We you are audible, and the slide is on introduction to engineering design second.
Yes, yes. Actually, my concern is your voice as well as my voice both are echoing. I'm just listening myself like that.
So there is no problem.
Okay,
It
okay.
is clear.
So, what I was saying that chemical engineering design one we have already done, and if you see any equipment, whatever the after of that, that we have already done in class. Now, this course we will basically go deeper into the equipment that you can understand. Okay. So this code is EC701, chemical engineering design 2. So before going into what exactly this subject will give skill as far as chemical engineering is concerned, okay, before discussing that, I will quickly cover what the chemical process and what is the meaning of designing. Okay. So if you see any chemical process, chemical process means, if you need to develop uh, any product, okay, chemical process we call when we have product from raw material. So it has six different steps. Okay, number one, conception and definition. Okay, conception, I see that I have an idea that I want to make that product, particular product. Okay, so I have that concept. Okay, so it means I already decided based on market survey, public comment, whatever you can see. Based on that, I have already decided that this product I would like to make. Okay, and conception is the idea. Definition is basically how I will do it. Okay, to make any product, you can could have number of ways. Okay, choose a particular way that we can say the route has been defined. So I hope you understand the difference concept as well as definition. Concept is to decide the product which you want to make. Okay. Definition means like how we will make that product. Okay. So in that we can say that you have already the initial idea and how to implement that idea. Okay. Once you define the route, you need to go for the second step, which is flow sheet development. Sheet means like uh, how your process will continue from raw material to product. Okay, what would be the units involved in that? How those units are connected? What could be the inlet? What could be the outlet? Okay, what could be the final packaging and all? Okay, so from raw material to the final product or packaging, I can say, what would be the route you have already decided in definition. So, based on that, you can decide, you can prepare the and that preparation is called as the shipping development. Okay, I hope you understand what I'm trying to understand on. Conception, you have definition you have done, based on that flow sheets you have done. Okay? And once you have done the flow sheeting, you already have the idea are the equipments which are placed in the flow sheet. Either it could be reactor, it could be your separator in the sense like distillation column, whatever. Any heat exchanger could be there, pumps could be there. Okay, so flow sheeting will tell you what exactly equipment you need in flow sheet. Okay. Then third steps come that we have to design those equipment. Okay. Uh, and what is the meaning of this that we will discuss course is all about. So, equipment you already have decided, and then we need to do the design. Okay, design. If I take over here, it means to decide its dimension. Whatever design you have done previously, okay, in the last semester. If you recall that here we have already discussed that dimensions are already available with you. Okay, if you need to design a tall vessel, you need to design pressure vessel, anything for that dimension you already have. Okay, that could be your diameter, whatever. Okay, but here you will decide those dimensions. Okay, so this course will particularly deal with that concept of design. Okay, so you have a flow sheeting, you have already decided the equipment, then you can design. Once you design this, okay, then you can do economic analysis. Economic analysis means like if I consider equipment to be the economics involved in um, manufacturing of that equipment, installation, functioning, everything, okay, to bring it to the operation. Okay, what cost will be involved that you can consider as economic analysis, along with whatever cost will be involved to run that equipment. Okay, which will in raw material, electricity, everything. Okay, so once you decide the uh, its dimension and all, you can go for the economic analysis. So you can do the economic analysis of the whole process, okay, including the selling of the product. Okay, then only the idea whether that would be or whether that product would be beneficial for you or not. Okay, so if you do the economic analysis, you have the basic idea that this much in uh, amount you need to invest. Okay, so once we do that economic analysis, then we can optimize. Optimize, okay. Optimize. Let's say you need to optimize the production. Okay, total production capacity need to optimize, uh, or best thing to optimize is the economics. Okay, because if I'm having a profit from the product, from selling of the product, okay, and if profit would be maximized, you would be very okay. So we can say that optimization will be considered, that is basically optimization of the profit or minimization of the losses. Okay. Optimization means maximizing profit or minimizing loss. I hope you understand my point. So that we consider in optimization. It means in all way you have you consider the best process. Okay, as far as economics is concerned, as far as design is concerned. Okay. Now, once I'm having all these parameters, we can do the reporting. It means you need to prepare the report, right? To convince that yes, I'm having a profitable process. Okay, I designed the profitable process. Okay. So these are six different steps to design a process for any given product. Okay, but here in this particular, we will consider a step that is design of equipment. Okay, so design of equipment uh, we need to consider and um, how we will see that how it would be beneficial for chemical process. Okay, so let's continue with design of the equipment. And here I have the onion diagram. If you recall the last course, from onion diagram only started. Okay. So here I'm also having the only discuss that in detail. Within that you are already aware of this. Okay, because we have already done in the last same thing. Just quickly I will cover this. Okay. So if you see the onion diagram, basically layers inside. Okay. So uh, through this diagram, represent chemical process very easily. Okay. So as I told you that we need to produce make any product, so that product will be made from the raw material. So raw material has to react to give product. So the primary unit over here in any chemical process is the reactor, and we consider that as a core of the reactor. Okay, so let's say A plus reacts and gives C plus B. Okay, so once I'm having this reaction, I could have C plus D. So if you see, this is reactor, and then once I'm having this reactor, we can have C and D that would be separated. So separator would be the second layer. Okay. So I'm having reactor, I'm having this reactor. Then once I'm having the separator for the heating and cooling requirement, as we see over here. Okay, heating and cooling and these exchangers. Okay. So once I'm having the separate, we can heat exchanger network. That heat exchanger network, we consider different exchangers in this. That may be like process heat exchangers, as you can see over here, or we can have the heat exchangers which involves the utilities like have condenser, have reboiler. Like once having this heat exchanger network, some of the heating requirement would be met the process only observed over here, but some of the requirement to satisfy from outside to supply the utilities. So obviously utilities layer will come after this exchanger network. So once I'm having this utility, we need to generate that, and that we had the site. Okay, either you can have the steam production or you can have the steam tower to have production. Okay, like that. So this is the whole orient diagram or we can say whole chemical process, layer to layer. Okay. So my emphasis here is to let you know that in this particular course, okay, if you read this particular course, what skill will be developed in you so that you can contribute in this chemical process, okay, or we can say that you can contribute in this Venn diagram. So we will see over here the equipment which we need to design, what equipment we will consider, and where these equipment will be helpful to helpful in chemical process. Okay. What or we can say in which layer you can contribute by reading by studying this particular course. Okay. If you have any confusion, you can let me know also. There is no issue that I keep on speaking and people will listen. You can tell me if you have any confusions. So equipment we need to design very important equipment for this chemical industry is concerned. We have shell and tube heat exchanger. Okay, if I say for chemical plant, most widely used heat exchanger is heat exchanger. So that design you should understand, okay, properly. So first one, shell and tube heat exchanger. We have another heat exchanger that we consider as the condenser. Okay. We have to design the over here to design evaporator. We have to design distillation column as well as pack column. So all these major equipment we need to design in this particular course. Okay. And this is the Onion diagram which we already discussed. Okay, if I consider this innermost layer, uh, we can say that this is the core and numbering we have done from outer, okay, not from the inner, okay, so that you can see. Now, as far as I believe you understand each layer. The fourth one is this, we can say, reactor. This is separated. This is heat exchanger. This is okay. So as far as shell heat exchanger is concerned, once you understand the design of this, you can put in heat exchanger network there. Okay, you can design any, you can design heat exchanger or shell in tube. Yeah, I'm not saying any heat exchanger, but this particular heat exchanger capacity. Okay. Condenser you can design, which is again the which is again the heat exchanger. Once you do that, you can contribute at second layer. Okay, diagram. Evaporator in when we consider, I don't know how to take that evaporator. This is basically used to take solvent from the slurry. Okay, solvent from the to get more concentrated product. Okay, this is concentrated slurry. I hope you are able to. I don't understand. It is giving problem to you or not. Are you able to understand?
Yes, ma'am.
Okay, okay. So because I'm feeling disturbance in myself, I, that it is giving disturbance to you as but I can't. Okay. So as far as are you saying something? Okay, okay. So this evaporator what we have uh, this over here is it takes the solvent from the slurry to make more slurry. Okay, so when we consider the that it takes the solvent that is done through heating. Okay, so if when we consider this evaporator in detail, you can see that heat exchanger is a integral part of this evaporator. Okay. So it will exchanger layer as well as separate layer both, because it has to separate the solvent from the slurry. So how it is separated and how it is and all that we will cover in evaporator, and so you can understand that which you can contribute in both the layers, in separator as well as the evaporator. However, when we distillation column, both of these are used as a separator, okay, to separate the components. Okay, back column you can just an absorption column and all column like that. Okay, so all these equipment we will discuss in detail in this course. Okay, and once you have the uh, design idea, all these equipment can very easily contribute to engine, chemical, what we can say, chemical processing, chemical process. Okay. So, design skill will be developed in you. However, the complete design, when any equipment, that will be done together with this subject as well as previous design subject. Okay. So, these are some of the equipment and the meaning of designing, as we have discussed in the last semester as well. Thickness of different component of the equipment is to be calculated, but here it is not is to be calculated, that you already know. What we need to do for such designs, dimensions of equipment are usually known. So here we need to reverse. Okay, reverse in the sense like thickness of different equipment. I believe you know already. Uh, Not the value, you know to calculate that. Okay. However, in this course, we need to discuss, we need to fix the dimensions of the equipment. Okay. If I consider the heat exchanger, LNG type, the design will be the length, the heat exchanger, the length, diameter would be the inner accessories. Inner accessories means your what we can say the tubes, okay, tube support, okay, baffles, all these how you need to consider in design, that we will study over. Okay, so dimensions you need to decide now, and then you can calculate the thickness of different equipment based on the previous course. Okay, so that is the meaning of designing. However, this particular course, that is chemical engineering design 2, where meaning of designing is little bit more what we can say, specified, okay, with respect to the equipment. However, you need to decide the dimension only, but we consider the meaning of designing in slightly different way. How? Let's see that. So here I'm having the equipment. The first one is the chilling heat exchanger. We have the condenser, the boilers. All these are heat exchangers. Okay. The meaning of designing over here to calculate total heat transfer coefficient and pressure drop. Okay. Uh, and once you calculate the overall heat transfer coefficient and pressure drop and bring it to the feasible range, okay, bring it to the feasible range, you already fix the dimension. Okay, let's say your heat exchange, sorry, heat transfer equipment will not in the range. Okay, particular given dimension. Need to revise the dimension to bring it to the what we can say feasible range, right? What that is, how to achieve that, all we will discuss. Here, the design you need to bring the overall heat transfer pressure drop to a feasible range, and accordingly, the dimension of it will be fixed. I hope you understand my point. Okay. Next, when we consider this evaporator, in that the meaning of design is calculate the steam consumption and heat transfer area. Okay, heat transfer area, like I told you that the evaporator heat exchanger is the integral part. Okay, so what would be the heat transfer area of that heat exchanger that we need to consider in design with the steam. Okay, so that is about it. Next we have the distillation column, and in this distillation column, we need to calculate the ideal number of days. Okay, uh, that probably you have already read in mass transfer. Okay, using the method. I remember. Okay. So using McCabe-Thiele method, you already calculated the ideal number of days, but that is only for binary system, right? Here in this distillation, we will bring you to a little deeper into that calculation of trace, calculate that for multi-component system, right? So we need to find out the ideal number of trays. What could be the methods for that we will discuss. Then we need to go for the plate efficiency. Plate efficiency, you can say that you have already done. Like multi plate efficiency, you must have read. Column efficiency, you must have read. But here, all these you will read in different way. What is the way in terms of design? Okay, what could be design parameters? All these will be involved in this efficiency. Okay, so that would be different than what you have read. Okay, and lastly, if we consider plate hydraulic parameters, it means single plate to design. Okay, so that is about the distillation column. Lastly, we have the pack column. For this, we need to calculate the height, means bed height, diameter, and column internal features. Okay, all these we will discuss in as far as design is concerned in this CE 2. Okay, so I hope you have enough idea or what I can say, you have enough knowledge that why you are studying this course. Okay, what skills would be developed, how it would be beneficial for a chemical process, being a chemical engineer, where you can contribute while reading this particular course. So I believe that idea uh, you have got by now, and we will go for the designing from uh, what we can say next after a few minutes. Okay, so here we have the basic book to consider in design. So that we have volume Richardson Wilson volume 6. Okay, and I will recommend you to have fourth edition of that. People get recent edition like sixth edition, seventh edition like that. But in that, many things are not available, which we cover over there. Okay, so fourth edition would be perfect for this. Okay? And if you don't have that, share that the soft copy. And second, we will follow RW book, okay, which is heat transfer, basic about the heat transfer. Okay, so these books will be followed for this. And if you can find them, it is fine. Otherwise, let me know. I will share that because soft copy of both books are available with me. Okay. So that is about particular introduction. And just 2 minutes, I will start the second of that. Okay. Okay. Just give me 2 minutes. I will read. Okay. Nirajan or any.
Yes, ma'am.
Okay. Okay. Just give me 2 minutes. Okay.
Okay, ma'am.
Thank you. Hello. Hello, Nirajan. Am I audible? Hello.
Yes, ma'am. You are audible.
Okay. Thank you. So, I will share the screen. Okay. I don't know what is going on. So I hope the screen is at PPT classification of heat exchangers.
Excuse me, ma'am, your voice is a bit disturbed.
Sorry.
Your voice is a bit disturbed, ma'am.
My voice is not coming. What you mean?
It is slightly cracking, I guess.
The screen is visible.
Yes, ma'am. It is.
Now,
Yes, ma'am. The voice is also clear right now.
okay, PPT mode, can you read the content?
Yes, ma'am.
What it is?
It's on first page, classification of heat exchangers.
Very good. So, I think you are able to see that. So, as we have discussed in the like 2 minutes back, like in designing, we will cover some of the equipment. But the first equipment there was shell and tube heat exchanger. Okay, so uh, here before starting the design directly design of shell and tube heat exchanger, I will tell you brief about the classification of heat exchanger and some important points we should consider uh, starting the design. Okay, so quickly I will cover the classification of heat exchangers. So we have this general classification of heat exchanger equipment, and as far as this classification is concerned, we will cover different, what we can say, different domains. Okay, so the first domain will be the classification according to transfer process. Okay. Uh, why I'm saying this classification? Because you should understand that what are the different heat exchangers and where these exchangers are okay, for your uh, in chemical process. Okay, so we will cover this classification before starting the design of shell into heat exchanger. So as I have told that I will cover that in different domain. The first is the transfer process. Transfer process, I believe you understand how the heat is transferring in the heat exchanger. So when we consider that, we have two different classifications of that. Number one, the indirect contact type, as you see over here, and secondly, direct contact type. So when I consider indirect type, it means the uh, uh, transfer of heat when I'm considering this should be within zone. Okay, one either ICC zone or ICC fluid, whatever in you can understand. But indirect type means two fluids should not be in contact. Okay, so one will be in one side, another fluid will be flowing in another side. So that you can understand that the indirect is there. How heat transfer will occur over there from hot fluid to separate separating wall which separates the two fluids. Okay, so from hot fluid to separating wall and then from separating wall to the cold fluid. As usually we see what we can say in double pipe heat exchanger. Okay, one is flowing in a pipe and the fluid is flowing at another side. Okay, so the separation of the fluid will occur with one separating wall. Okay, so that is indirect contact type. Direct contact type that you can understand there is no separation. Okay, what could be the example of that we will see. Further, we will classify the indirect type in direct transfer type. And second is type. Okay, direct transfer type means uh, let's say I'm having two fluid flowing in a double pipe heat exchanger. Okay, so heat we transfer from hot fluid to the separating wall and from separating wall to the cold fluid. Okay, so that is basically direct transfer type. It means heat will flowing from its natural tendency from high temperature to low temperature to the wall, right? So that is direct transfer type. Storage type will be heat will be stored in some what we can say in what in some accessory, and then the heat which is stored in the accessory that will be transferred to another fluid. So how it will happen? Like I'm having the heat exchange in some packaging is done. Okay, so in one go, we can say in one first step, the water fluid will go that package. Okay, transfer its heat to that package and then exit. Okay, in second is cold fluid will enter to that packing, take heat from that packing and then exit. Okay, so we consider that as a storage type. Okay, further we classify direct transfer type. That could be single phase, that could be multi-phase. Single phase, like when I'm considering sensitivity transfer. Okay, so that could be the single phase. If water is
Excuse me,
there,
ma'am.
hello, saying something?
Ma'am, you sound like that.
There is some issue, this problem, huh?
Yes, ma'am.
Mm, you are not able to Follow?
Yes, ma'am.
Are you able to follow what I'm saying?
No, ma'am. Sound is disturbed.
Too much echo is there. I'm also not able to understand what you are saying. Mm, hello?
Yes, ma'am.
It is fine, I hope. Now? Are you able to see my video? I just kept the camera on.
Mm,
No?
No, man.
your sound is lagging a bit. I think due to internet problem.
Yes, yes. Understand how to resolve that. I kept the camera off to uh, have better connectivity.
It will be alright for some time, but when you start teaching, it gets lagged.
Nice. Okay. So only up to you could able to listen. Nothing.
Storage type of heat exchanger.
Which part? How to resolve that actually the problem is. Hello? Is it
Yes, ma'am.
audible now properly?
For now, it is audible.
Huh?
For now, it is audible and
It is all
clear.
right. Huh? Should I start?
Yes, ma'am. We will let you know if there's any problem.
Okay, okay, okay. Now voice is echoing again or not? Voice is
Mm,
clear.
yes, ma'am.
Okay, okay. So, we were at storage type, right?
Yes, ma'am.
Uh, Storage type you have you could listen or not?
Uh, you are
Or
audible, ma'am.
huh? Should I start from storage type?
Yes, ma'am.
Okay, okay. So if you see here, I'm having indirect contact type where further it is classified as direct transfer type and storage type. So, direct transfer type that we have already discussed. Storage type means we need some media, we need some means to store the energy, to store the heat. Okay, and then that heat would be transferred to wherever it is required. Okay, so how we can do that? Let's say if I'm having a heat exchanger where packaging is done. Okay, so that packing would be like it is used to store the heat. So how it will store the heat? Like hot in one step, hot fluid will follow, hot fluid will enter into this, and then hot fluid will transfer its heat to the packing. Okay, then it exit the heat exchanger. Secondly, in second step, cold fluid will enter, it will come in contact with that packing, takes heat from the packing and then exits. Okay, so I hope you understand that here packaging or some media we need to consider to store the energy. Okay, so energy will not be directly transferred. In one step it will be stored, in second step it will transfer to the desirable what we can say purpose. So that is the storage type. Further I will discuss that in detail. But let's classify direct transfer type. So there I am having two things like single phase as well as multi-phase. Single phase, you understand, that is when I am having sensible heat transfer, and multi-phase when I'm having change in what we can say the phase. Okay, single phase means if I'm considering water, it will remain water. But in multi-phase, when I'm considering water, it will convert into the steam. Or if I'm having the steam, it will condense and then water will liquid I'm having. So that could be single phase as well as multi-phase. Further, when I classify direct contact type, direct contact type could be like within immiscible fluids. Okay, when two fluids I'm having which are not what we can say, which will not mix together, so heat can be transferred from one fluid to another fluid by direct contact. Okay, no separating wall will be there. Gas liquid. Okay, second is the gas liquid that you must have observed very like near to you, like what we have air coolers. Okay, so air coolers, what happens that in the fence the liquid will fall from the top. Okay, and in what we can say, there is an exhaust wall, exhaust fan, it sucks the air, and then through that what we can say the fins, the heat transfer occur between gas and liquid, or we can say air and liquid. Air becomes cooler and then it throws through the exhaust fan. Okay, so in that way we consider direct contact type. There is no separating wall between the two fluids. So one domain we have already done, that is transfer process. Second, we are classifying according to the surface compactness. Compactness, if we consider, compactness means how what we can say, how we are placing larger and larger heat transfer area in smaller and smaller volume. I hope you are getting. Okay, surface compactness means what we are compacting is the heat transfer surface. Okay, so that will be classified as gas to fluid and liquid to liquid. Okay. So here, when we consider the compact, the compactness we usually define with this beta. Okay, and this is basically heat transfer area in a unit volume. Okay, so when I'm having more and more heat transfer area in a unit volume, it means that that unit will be called more and more compact, and that will be used for transfer of heat. So if beta is more than or equal to 700 meter square per meter cube, that we consider as the compact heat exchangers. Otherwise, it is non-compact. Okay. So when I am considering gas to fluid, this beta value will be more. However, when I am having this liquid to liquid, beta value would be less. That would be, we consider that limit as 400, but that is 700 in case of gas to fluid. And the reason you could understand, like when I'm having the gas, it is more compressible than the liquid. Okay, so we can compress more and more air in a smaller volume in comparison to liquid. So compactness would be lesser for liquid to liquid in comparison to gas. Okay, If you ask that what type of heat exchanger these are, so these are very small type of, okay, if you see the size of that, it is very small, and these are used when we are having the surface constraint, when surface is not available in significant what we can say larger amount or larger value, we can have this compact heat exchanger. To give an example, like aerospace, okay, where space is literally limited, and there we consider the compact heat exchanger. These compact heat exchangers are used in cryogenic conditions also, okay, where that conditions are very severe, and that cannot be what we can say cannot be placed in a larger area, so we consider compact heat exchangers there. Okay, so these are some of the application, and when we consider the compactness, we want to like aerospace, if I am telling, their space is a constraint. Along with that, weight is also a constraint. You cannot put very heavy machines there. Okay, aerospace, that we need to bring it to the like above atmosphere, so that we can consider um, compact heat exchangers. And as far as weight is concerned, we usually consider lighter weight of manufacturing, like aluminium instead of steel, instead of copper and all. Okay, so the compact heat exchangers are usually made with aluminium. Okay, and size I have already told you, and application as well. So these are some of the classification based on transfer process as well as surface compactness. And next category we have is the classification according to the construction. Okay, so here I'm having classification like tubular heat exchangers, we have plate type heat exchanger, extended surface heat exchanger, and we have regenerative type. Okay, so let's start with tubular type. These will be further classified as double pipe heat exchangers, shell and tube type, spiral tube, and pipe coils. Okay. As far as this tubular type classification is concerned, um, you can understand, like when we have discussed previously, for transfer process or compactness or this construction, heat exchangers are overlapping between them. Like here I am considering double pipe heat exchanger, it will again fall in the what we can say transfer process, where indirect transfer we are discussing. Okay, so these exchangers will be overlapped between different domains. So double pipe heat exchanger, that you can you already know. I don't need to discuss that much. Okay, in detail. Shell and tube type, that you already know. We have shell, we have tube bundle, and tube bundle are inserted inside the shell. Okay, so that is shell and tube type. When we consider double pipe heat exchanger and shell and tube, both are considering what we can say one pipe and one pipe, and inside that we have another pipe, that is a double pipe. But inside that, if I'm having number of pipes, we can consider that as shell and tube type. Okay, so this is a tubular type of spiral tube. When I'm considering spiral tube, mm, how you can consider that spiral tube? Spiral tube will be like just a moment. Okay, let me start camera, if it will work. this spiral tube will be like, are you able to see my camera?
Yes, ma'am.
Okay, okay. So if I consider the spiral tube type, this you can see it will be on this surface only, like a spiral type. Okay, you must have seen the coils. I hope you understand that coils which we usually consider for mosquito as a mosquito repellent. Okay, so the type of that coil we consider this spiral tube heat exchanger, smaller diameter, and then diameter will keep on increasing. Okay, diameter of the tube will remain as it is, but the placement of that will keep on increasing. Okay, so when we consider a spiral tube heat exchanger, that would be coils type and it will remain over the surface. Okay, at the horizontal plane only, not on the vertical plane. I hope you are getting my point. So let's say if on one plate I am having the water, okay, and I put the spiral type of heat exchanger in this tube, and we can have another fluid which maybe you can say the steam, like that. So steam will get condensed by transferring its heat to the water. Okay, so this spiral tube type would be like only it will spread horizontally, not vertically. Okay, so that we can consider as coiling, but coiling will be on surface only. Okay, another I'm having the pipe coils. Pipe coils you can consider as helical type, like this. Okay, it will move if I'm having one cylinder, and around this you can have the wound of pipe that we consider as pipe coils. Okay, so pipe coils will be helical, spiral tube will be like coiling at the horizontal surface as well, as horizontal surface only. I hope you are getting my point. So in that way we can consider the tubular heat exchangers, and if I consider shell and tube type, these will be further classified as cross flow to tubes and parallel flow to tubes. Okay, cross flow, parallel flow, you understand, right? It may be co-current, it may be counter current. So if I'm having shell and tube heat exchanger of multiple passes, we can have parallel tube, sorry, we can have parallel flow. Either it could be counter current or it could be co-current. Okay, but what will happen in cross flow? Okay, is it possible in shell and tube heat exchanger? Yes, it is possible. How? Like if I'm having the heat exchangers, let's say you consider this as a heat exchanger, and when I'm having this shell, okay, when I'm having this shell and inside this I'm having the tubes, okay, what will happen? Here I'm having the nozzle, okay, so fluid will enter into this, and whatever fluid is flowing in the tubes, okay, fluid will flowing in this direction in the tube, and in shell fluid will flowing in this direction. So there will be a cross flow tubes. Okay, so if I'm having the bunch of tubes and shell length is not significant, there will be a cross flow tube, cross flow type. Okay, otherwise that will be parallel tube. But in a common heat exchanger, when I'm having significant length, okay, here I'm having the cross flow, as well as once I'm having the cross flow, the fluid will move in this direction. Okay, so there will be parallel flow. So usually in shell and tube heat exchanger, I am having cross flow, co-current flow, and counter current flow. All three exist together. Okay, so that we can consider all these flow and all that also we will consider what we can say later on in detail. Okay, so that is about the tubular type. Next, I am having the plate type. Plate type heat exchanger, when I am saying, this is the first one is PHE, that is plate heat exchanger, and second is the printed circuits. Okay, that you must have seen the motherboard circuit over the motherboard. So that type of circuit we can have for minor chips and all, so that we consider as the heat exchangers. Okay, so as I'm having the very fine what we can say wiring, uh, so that we call as a circuit, okay, over the plate, or over the what we can say surface, that we consider as the heat exchanger. Okay, so that is the plate type. More precisely, the plate heat exchanger would be of three types. Okay, so these three types are gasketed, welded, and brazed. Okay, gasketed means that also we will discuss in detail about the for this plate heat exchanger. Gasketed means we place the what we can say the gasket between two plates. Gasket, you understand, na? That is basically the what we can say the separating material, or we can say normally we call that as washer and all. Okay, so if I'm having these two plates and I need to keep these two plates at a certain distance, in between I put a gasket. Okay, so that gasket thickness will decide that how much these plates would be departed, would be kept away from each other. Okay, so that is gasketed type. I will let you know the this these type of heat exchanger. It's schematic also, so that it can be more clear to you. Okay, so gasket type means between two plate we need a gasket to, or we need what we can say rubber kind of a washer kind of material, which will provide the definite space between two plates. Okay, and instead of gasket, if we do a permanent joining between them by welding, okay, the benefit of gasket is only this, that it can be removable. Okay, or it can be what we can say assembly can be reassembled. Okay, by putting the gasket apart, by we can have plates, separate plates. Okay, however, when I consider the welding will give the permanent joint, and these two plates will be permanently joined to each other while keeping a definite space between the two. Okay, so that would be welded. Brazed, that you can understand that in welding we usually consider iron material to fill the gap. Okay, if that gap is filled with the brass, not brace, with the brass material, we call that as brazing. Okay, the brazing is usually done when you must have seen utensils at your home. Okay, if I'm having the bowl and the handles of that, if I consider steel bowl and steel handle, that can be joined by brazing. Okay, their welding is not done, okay, in steel. So that could be different type of plate heat exchanger. Next, I'm having extended surface heat exchanger. That could be plate type, that could be tube type. So plate type means I'm having a plate in which tubes will be inserted. Okay, so that could be, you must have seen the double pipe heat exchanger with fins. Okay, annular side we have the fins like the what we can say the strips are welded. Okay, in the annular side. Okay, or more precisely if I say is that vertical strips are welded over the outer part of inner pipe. I hope you are getting outer part of inner pipe. Okay, so if I'm having this tube, inner tube, so is what we can say is strips will be welded like this. Okay, this also I'm considering the tube type, but don't consider this as a tube type. This, please consider this as a plate type. Okay, so that plate would be welded over here, welded over here, welded over here like this. Okay, so along the outer periphery plate will be welded at a regular interval. Okay, so that we call as fins. Okay, plate fins. Okay, tube fins, when I'm considering, you must have seen the CDs. Okay, the common compact drive which we are considering in our computer. So if CD will be will be placed over the tube. Okay, if this is the tube, we put the CD. Okay, one over here, another CD will be here, another CD would be here. So that we consider as tube fins. I hope you are getting my point. Okay, plate fins, strip will be welded, tube fins, what we can say, disc will be welded. Okay, and another I'm having the regenerative. So regenerative would be like storage type. Okay, so just a moment, please. Sorry. Hello. Okay. हाँ please हाँ मैं आ जाऊँगी ठीक thank you sorry so these are some of the classification based on construction type, and we can have a classification according to heat transfer mechanism as well. And here I am having different mechanism. The first one is the single phase convection on both the side. Both the side means here I am considering with respect to heat exchanger, with respect to indirect heat exchanger. Sorry, that could be double pipe, that could be shell and tube, okay, whatever. So single phase convection on both the side, it means convective heat transfer occur in both the fluids, so that we call as the sensible heat transfer in both the sides. Okay, second is single phase convection on one side and two phase convection on other side. Okay, let's say one side I am having water, another side I am having steam. So steam gets condensed, so there will be two phases of one side. Okay, and one side water is there, so single phase convection will be there. So that could be your condenser. Okay, second, I'm having two phase convection on both the sides. Let's say if I'm having phase change in both the sides. Okay, one side steam is there, another side let's say your liquid is there which is available at boiling condition. So it will take the heat and boiling will start and phase change will start at both the at one side, another side condensation will start. Okay, so two phase convection on both the side means the example you can consider as reboilers. Okay, and here I'm having combined convection and radiative heat transfer. So here we can have like boilers. Okay, combined convective and radiative heat transfer. So we can have the fire at the boiler, you understand, right? At the center we have the burning of the fluid, combustion will occur. Okay, and at the what we can say inner periphery we have tubes. Okay, inside this tubes water flows. Okay, so this water gets heat from the burning which is happening in between, burning which is happening at the center. So we have convection as well as radiative heat transfer, so that we can consider as the boilers. Okay, so these are some of the classification, and we will discuss some of the equipment which are commonly used in chemical plants, and a little bit detail we will cover, and then we will go for the designing of shell and tube heat exchangers. Okay, so today I will stop over here. We will continue in next class. Okay, so next class, tomorrow I won't take the class, that may be day after tomorrow at the same time, 11:30 to 1. Okay.